Okay guys, in this video we're going to look at how we actually calculate all of the forces given a 100 Newton force or any force applied to a particular system or a particular truss. So here you have the diagram for this particular scenario, and in that diagram you need to be given what the force is, where it's applied, and what the dimensions of the actual truss are, or the dimensions of the triangle for us. So in order to do this, that's what we need to be given. So let's take a look. So step one is calculate all the external forces acting upon the joints. What we do is kind of simplify the diagram. We can simplify this diagram by just drawing triangles, essentially. Taking the actual diagram and converting it to triangles where we have all the dimensions here. And then the biggest thing here is make sure you establish where your pin and your roller are. Hopefully this process is review for you at this point, so let's go ahead and go through this process. All right, so we want to figure out what all the external forces are. So we know that the external forces at our pin, we're going to have a force in the y direction. That's F at A in the y direction. We're also going to have a force in the x direction. That's F at A in the x direction. We've got our 100 Newton force acting downward. And then over here at the roller, we've only got one vertical force, F at C, in the y direction. So let's go through this calculation. The first of our equations that we want to use is the sum of the forces in the x direction has to be equal to 0. So we look up in our diagram and we see that so far we only have one force in the x direction. So the force at A in the x has to be equal to 0, and we're done with that one. Next one that we want to look at are the sum of the forces in the y direction. Those have to add up to 0. So we've got the force at A in the y direction. That's acting in the positive direction. We've got this 100 Newton force coming downward, so minus 100, acting downward in the y direction or in the negative y direction, and then the force at C in the y direction is a positive force, so we get the force at C in the y direction is equal to 0. Two unknowns here, so we're not going to be able to solve, but we can simplify a little bit. So the force at A in the y plus the force at C in the y, these are the two reaction forces, have to balance out with the force. We're just moving this 100 over, so add 100 to both sides. Have to balance out with the force acting upon the truss. So we're going to come back to this and plug some stuff in. The last one is the sum of the moments, or the rotational forces, and technically this is about A, or about that pin joint. So let's go ahead and add these up. So we have the force at A in the x. And again, remember when we do this relative to the pin. So how far is this thing from the pin? Well, this thing is at the pin, so it is 0 times the force at A in the x. The force at A in the y, similarly, is right at the pin, so it's 0 times the force at A in the y direction. Going up here, we've got our 100 Newton force. First of all, it's acting in a negative y direction, or downward, so we need to subtract it. And we also need to account for how far it is from the pin. So this is this dimension right here. It's 5 away from the pin. And it's 100 newtons. And then the last one is the force at C in the y direction. That's a positive force, or a force in the positive direction. It is 10 units away from the pin. And all of those have to balance out to equals 0. So let's go through and simplify. 0 times anything is going to drop these two forces off. We're left with negative 500 plus 10 times the force at C in the y. That's equal to 0. A little bit of algebra here. 10 times the force at C in the y is going to be equal to 500. We add 500 to both sides. And so the force at C in the y direction is going to be equal to 50 newtons. So we solve for that force. We know how much force is being applied there. Take that value and plug it up into this equation here. So we're going to get the force at A in the y direction plus the force at C in the y direction equals 100. Force at A in the y direction plus, we know the force at C in the y direction is 50 newtons. And that's equal to 100. Go through and solve, and you find the force at A in the y direction. Subtract 50, that's also 50 newtons. So we've solved for all of the external forces, and that's the first step in calculating all of the forces as they come together for this particular truss. All right, so step 2 in this process is to calculate all the angle measures for each joint. Now we're using a really simple one, but I'm going to take you through the process of how we go ahead and do that. The angle measures that we're interested in are this guy, call that theta 1, and this guy is theta 2. So we look at each joint and we take into account the measures of the triangle that we've created. So if I draw this triangle over here, here's theta 1, and I know that the height of that thing is 5, and in the x direction, the base of that thing is 5. So I'm going to use my trig function. So I know this relates the opposite to the adjacent. So the tangent of theta 1 is equal to 5 over 5. Now obviously when we get into more difficult or complex triangles, ones that aren't necessarily isosceles and basic like this one, we're going to have some different measures. So you want to make sure that you go through this process in order to calculate the angle measures. All right, solve for theta 1. We take the inverse tangent of both sides. So we get inverse tangent of 1 and plug that into your calculator, and you get that theta 1 is equal to 45 degrees. So that is the angle measure of this particular angle where these two members, AB and AC, are coming together and connecting. We do the same thing on the other side, so we want to draw that triangle out. This is theta 2. And again, we've got a base length here of 5, a height of 5. That's the opposite over the adjacent, so we're going to go through that same process. Tangent of theta 2 is equal to the opposite over the adjacent. Theta 2 is then equal to inverse tangent of 1. And plug it into your calculator, and you should get that theta 2 is equal to 45 degrees. All right, so we've got the angle measures here, and I've kind of simplified the diagram here. The last part of this, and this is really the intensive part, is we want to create a free body diagram for each joint in order to figure out how much force is being applied to each individual member. All right, so let's start with joint A. And we start with joint A, and the free body diagram for joint A looks like this. So you can see I've highlighted joint A. The red forces in my diagram are the external forces, and we already solved for this one. We know that this is 50 newtons. We know that the force at A and the X is 0. And we've got some other ones that we need to account for. All right, so at joint A, we're going to look at the sum of the forces in the X direction, and we know that they've got to balance out to 0. So first of all, we've got the force at A in the X direction. Secondly, we've got the force at C, the force of AC in the X direction. So that's this member down here, AC, that bottom member in the X direction. And the third part is what we talked about before. We need to figure out, this is a diagonal force, and so this diagonal force is going to apply force in both the X and the Y direction, and we need to, under this particular equation here, we need to account for how much force is being applied in the X direction. So if you remember back, this is really just figuring out the X component of this thing. So if I want to figure out the X component, or an expression for the amount of force that's being applied in the X direction, I've got my 45 degree angle. I know that this is AB here, and so an expression for the amount of force that's being applied in the X direction is going to be AB times the cosine of 45. All right, so hopefully you're comfortable with that. That comes from the fact that we know that the cosine of 45 is going to be equal to whatever the X is over the hypotenuse. and then multiply both sides by AB, and you come up with this expression. So we need to figure that into what we're doing here. This is the force of AB in the x direction, and that's our last force in the x direction for this particular one. Simplify a little bit. We know that this is 0 from our calculations before, so that drops off. And so we have an expression that looks like this. The force of AC in the x direction plus AB times the cosine of 45 is equal to 0. Okay, so we've got two unknowns, so we have to stop there. I've changed this to blue so we just keep it consistent throughout the video, and I'll do the forces in the y direction in green. So we've got two unknowns here. Can't go any farther. We'll come back to that hopefully and figure something out when we're solving for the forces in the y direction. All right, so going back to our free body diagram, we've got the force at A in the y direction, and we know that that's 50, so we'll plug that in a second. The only other force in the y direction for this free body diagram is the force of AB in the y direction. And again, this is really just figuring out that component. And so we know that it's the sine function that's related to the y. So we're going to take AB times the sine of 45. And again, if you're looking for where or how that was developed, we know that the sine relates the opposite to the hypotenuse. So the sine of 45 is equal to the opposite. That's our y component. Over the hypotenuse is AB. And again, multiply both sides by AB and you come up with this expression. So that is the amount of force that this diagonal force AB, this diagonal member, is exerting in the y direction. And so we have that. We need to incorporate that into our equation over here. So this is AB times the sine of 45. And that's the only other force in the y direction. So set that equal to 0. The sum of these two has to be equal to 0. We know the force at A in the y direction is 50. So we plug that in. We solve for that when we're looking for the external forces. Go through and solve. We have AB times the sine of 45 equals negative 50. So AB is equal to negative 50 over the sine of 45. Plug that into your calculator, and we get that AB is equal to negative 70.71 newtons. So that is the force that's being exerted by AB. That's the force on that actual member, this member AB, and be sure to account for that sign. Leave that sign. It's negative for a reason. We'll talk about why here in a little bit. Okay, guys, so we found AB, and now we're going to take that value and plug it in where we see AB up here, and what that allows us to solve for the force at AC in the x direction. So the force at AC in the x direction, let's go ahead and move that over to the other side. That's equal to negative AB is 70.71. So negative 70.71 turns out actually a little positive. So 70.71 times the cosine of 45. So the force at AC, use your calculator, is going to equal 49.9995, or because this is rounded, that's equal to 50 newtons. Alright, so we have all the forces at joint A, so let's go ahead and move on to joint C here. So there's my free body diagram. And let's go ahead and put a calculation. So let's see, we use blue. So let's stick with blue. So for the sum of forces in the x, those have to add up to 0. And we've got the force at AC, the force of AC in the x direction. And we're going to add that to the component, the x component of CV. So let's go ahead and figure this out. Now, there's a little bit different calculation to this, and it's important that you make note of this. So when you're calculating this, I can't draw a good triangle, I think you get the picture here. So we know that this is 45 degrees from what we calculated before. What we have to take into account, though, is when we're figuring out this x component,
is, remember that our vectors, the direction of our vector is based on starting at that horizontal axis and wrapping it around. So taking that into account, we can see that this angle is 135 degrees here. So there are a couple of different ways that we can calculate this, and you have to be cognizant of this when you're going through it. Now, first of all, this x direction is in the negative x direction. And so one of the ways that we can do this is we know that this is CB. So our hypotenuse is CB. So one of the ways that we can do this is we can either say this is going to be negative CB times the cosine of 45, or we can call that CB times the cosine of 135. And if you plug these two expressions in your calculator, cosine of 135 and cosine of 45, you're actually going to get opposite results. And so that's why we have to attach this negative on here. Okay, so we're going to use, we're actually going to use the negative. So every time that we look at one of these components, we got to make sure that we're dealing in the negative or the positive direction. For this particular one, it's in the negative x direction. So we're going to subtract CB times the cosine of 45. So those are all the components in the x direction. So they're equal to 0. Again, 2 unknowns, so we can't solve any further here. So let's move on to the sum of the last. My color didn't change there. Let's try it again. There we go. Sum of the forces in the y direction. It's going to be equal to 0. So let's take a look here. We've got the force at c in the y direction. We already solved for that. We've also got the force in the y component of this diagonal force, and we're going upward, so that's the positive y direction. So we don't necessarily need to account for the sine change there. So this is going to be CB times the sine of 45. That's the y component, that's in the positive direction. So we got, and those are the only two forces acting in the y direction, and amount that are equal to 0. So from before, if you remember, we solved for the force at c in the y direction was 50 newtons, positive 50 newtons, so let's plug that in. This is 50 plus CB times the sine of 45. It's going to be equal to 0. Again, simple algebra is going to give us that CB, or BC, you can call this either one, doesn't really matter, is equal to, we're going to subtract 50 from both sides, so negative 50, and then divide by the sine of 45. So negative 50 over the sine of 45. Plug that in your calculator, and we find that the force on CB is equal to negative 70.71 newtons. So we found that one. We can plug that back in over here. Again, make sure you keep that sign, it's important. And when we plug that in, we get the force of AC in the x direction minus a negative 70.71, so that turns into a positive. That's equal to 0. Move this over. So we get the force at AC in the x direction is equal to negative 70.71 cosine 45. And simplifying this in our calculator, we get about 50 newtons. It's going to round up to 50 newtons. It's 49.9995. So we solved for that guy. We solved for CV. This is the last joint that we would have to analyze, would be this joint up here. But if you take a look at what happened down here, we already solved for the force at BC, and that's the same force here as it is here. So we already know that the force at BC is negative 70.71. We also solved on the slide prior to this for the force at BA. So let's go take a look at that. The force force at BA or AB is also negative 70.71, which makes sense because we're applying that force directly in the middle. And then lastly, the force at AC, we already solved for 5 is 50 here. And again, 5 is 50 here. We actually didn't have to do this because we already knew what this force was. Okay, so let's take a look at the big picture. What we just figured out. And what we figured out was applying this to our diagram, our original diagram, using all of these different free body diagrams. We figured out that this force right here was negative 70.71 newtons. We found that this force right here, the force applied to this number PC, was also negative 70.71 newtons. And we found that this force down here was 50 newtons. And that is AC. So what we've done is we figured out all of these forces. The external reaction force here is going to be 50 newtons. 50 newtons here. That's going to counteract the 100 newtons. And the reason that these trusses work, again, this is kind of grand scheme of things, the reason that these trusses work the way that they do when they are more stable and they're able to take on more forces, they take a 100 newton force acting downward, and they distribute that force between the three members. Alright, so we've got this 100 newton force downward, and not one of these members is feeling all of those 100 newtons of force, or taking on